Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a problem with partial fractions. So we have a over z plus I plus b over z minus I equals 1 over z squared plus 1. And actually a and b are constants in this case, so we're going to be solving for them. So let's see how we can find a and b from here. And this is actually kind of like a two problems in one, because after we find a and b, I'm going to show you something else. All right, so stick till the end. So to be able to solve a and b, I'll make a common denominator. Hopefully you notice that if you multiply these two things from sum of two squares, we get z squared plus 1, right? Okay, great. So let's go ahead and make a common denominator then. Just multiply this by z minus I and this one by the same thing. And multiply this by z plus I and the same thing here. And then we get the following. In the numerator, we get az minus ai plus bz plus bi. And then at the bottom, we get z squared minus I squared, but that's z squared plus 1. Again, that's difference of, sum of two squares. Great. Now the denominators are equal, so the numerators should also be equal for all values of z, except for negative I and positive I. Of course, they make the expression undefined, so they are really bad values. So let's go ahead and put it together in a meaningful manner. Since these are polynomials, kind of, sort of, right? We're going to be able to set this equal to that. That's a constant. So I'm going to write this as az plus bz, put the z terms together, and then write this as bi minus ai. Bi and ai are constants, by the way. Don't think of I as a variable, it's a constant. And that equals 1. So the next thing we should do is, because these are polynomials that are equal for all values of z except for those that I mentioned, we need to just factor out and write the left-hand side as a polynomial in z. And that's going to look like this. A plus b, the coefficient of z, plus bi minus ai. If you wanted to make it a little easier, you could probably just factor out an I like this. Even though I is a constant, it can still be factored. Now, how are these values equal for different values of z? It can only be possible if because there's no z on the right hand side, so that's a constant. The left hand side also needs to be a constant, which means there should be no z, right? But there is a z, we can make it disappear. Hocus pocus and mathemagic, right? And then the coefficient of I, but there's no I, are we going to set it equal to 0? No. This is not a polynomial in I. Again, I is not a variable, it is a constant. So we're going to set the whole thing equal to 1. Be very careful, because sometimes people, mistakenly just set that equal to 0, and you obviously get a equals 0 and b equals 0, which is not true, by the way. So from here we get the following equations. A plus b equals 0 and b minus a times I equals 1. So from here we can deduce, such a nice word, right? B equals negative a and b minus a equals 1 over I. Now we need to kind of multiply by negative I, so we can kind of write it as negative I over negative I squared, which is 1. So this is actually negative I. In other words, the reciprocal of I is negative I, which means it's also the opposite, right? Great, because they're conjugates. Makes sense? So b equals negative I, and we know that b minus I is equal to negative I. So let's replace b with negative a. B equals negative a, I meant. Negative 2a equals negative I. You could definitely do a equals negative b. That would be more positive. But a from here is just going to be I over 2. And since b is the opposite, it's just going to be negative I over 2. So whatever I is, we don't know what it is, right? We only know its square and some other powers. But those are the coefficients we're looking for. And we were looking for a and b values, so we got it, right? A is equal to that and b is equal to that. So what does that imply? Let's go ahead and talk about the other thing. Since we set this equal to a over z plus I, or the other way around, doesn't matter, b over z minus I, and now we can replace a and b with those values. But when we do, we notice that there's going to be a 1/2, which we can take out. So let's go ahead and take that out. It's better if we do that because now we end up with what? I over z plus I, right? Makes sense? So this is what I mean. I hope that's not confusing because I'm very good at confusing people, by the way. But this is what I meant. If you take out a 1/2, then we're going to end up with I over z plus I. And then the second one is just going to be minus I over z minus I. Because b is negative, we have to put a minus sign there. Make sense? So what is so good about this thing, right? Why would you use this? Okay, here's the thing. Suppose you were trying to integrate this, right? Let's put a little dz and dz to make it dz. Now, when you integrate the right-hand side, what are you seeing? 1 over z plus I. Well, it's kind of like the ln, right? The integral of 1 over z is ln z, and let's just avoid the absolute value because I don't like it. But this is basically going to be 1/2 of I times ln z plus I. And by the way, we could also take out I, so why not? Well, actually, I could have done that at the very beginning, right? Anyways, so we could still do it now. This is going to be ln z plus I minus ln z minus I. It's kind of like the integral of 1 over z with an additional constant, but that doesn't matter because its derivative is 0. Make sense? So we got something like this, and we could probably write it as follows in a more compact form, because this is the ln of a quotient, so we can write it as ln z plus I over z minus I. Now this expression should be familiar to you if you're doing complex analysis or complex numbers. Definitely this is something that'll come up at some point in some type of problem. Anyways, but look at the left hand side. Take a good look. Isn't that our tangent? Yes, absolutely. If you just integrate this directly, or if you want to use z equals tangent theta as a trigonometric substitution, who doesn't like trigonometry, right? So that's going to give us arc tan z. In other words, these two expressions are equal, but there should be an integration constant. So should we add a constant on one of the sides like c or k so that these are true, or are they true without a constant? I'm going to leave that question open for you to think about and let me know in the comment section. But this kind of gives us an interesting identity. And you know, you can even do something like this, tan both sides, and you're going to get z in terms of something else. So the tangent of a complex expression turning into z. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.